Hey everyone, so welcome to our third part as we continue to go through taking a look at some different problems in standard form. So in this case what we have in this problem and the next couple are word scenario type problems, and for these sections you are able to use graphing technology. So whether it's going through Desmos or whether it's using graphing calculator or some other means of graphing. I would encourage that you go through and just kind of try to model the problem first so you can kind of get a sense of some of the important points in it, and then after that to start to come back and take a look at some of these questions. So we'll go through the problem and then I'll get you to pause the video and give it a try, and then come back when you're ready to go through the solution for it. So we've got a frog sitting on a rock and he jumps into a pond. So in this case we have our formula that's here, okay, and we have to keep in mind here that h of t stands for the height. Okay, so h is our height relative to time, whereas we've got time with the variable t and h for our height. So since it jumped, it can be modeled by the function that kind of looks like a parabola. So where appropriate, answer the following questions to the nearest tenth. And then we've got a couple of problems to go through. So you can see the one that's here, and then there's a couple more that are here to run through. Okay, so what I would encourage that you do is to model the problem, okay, by graphic calculator or some other means, and then try to answer each of the questions and come back when you're ready to go through it. Alright, so for the first part here we're going to sketch this out, and so the first thing that we really needed to do out of this thing was to identify our Y-intercept, because normally whenever we have time involved anywhere, unless otherwise told, time is always on your x-axis. So time in seconds is along our x-axis, and that leaves our height to be on our y-axis. So this thing kind of has a distance over time kind of feel to it, in terms of some distance being covered in height and a time being moved along. So in this case now we can take a look and we can see that we've got our y-intercept. If we make time 0, so at the 0 point, where is it at? It's at 25. So it would make sense for this maybe to count by tens or something like that. So 10, 20, 30, 40, and 50. Okay, and so if we counted by tens, 10, 20, 30, 40, and 50, then I could see that my y-intercept happens at 25. Okay, now at this point the frog then jumps, and so we need to figure out what that vertex is, or what that max height is. And luckily through that graphing technology we can take a look, or you could even do minus b over 2a with a calculator and you could figure out what the value would be in terms of how high up it would go. So if we were to use the graphing technology, we would see that the vertex of this thing happens at 0.153 seconds and 36.48 centimeters. Okay, so the whole thing, just keep in mind, is measured out in centimeters. So basically we're just kind of copying this onto from our graphing technology onto our plot here. So let's take a look and see what we should probably count by on our bottom part. Really, we're not talking about a long-term event here, like this is happening in terms of hitting the water. If I go ahead and look at the root of this, it's happening somewhere at 0.426 seconds. So if I had going by 0.1s, that would be lots. So 0.1, 0.2, 0.3, 0.4, and 0.5. Okay, maybe just a couple more just to kind of have a couple extra points to go by. So 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. So this thing hits a max height at 0.153 seconds, so roughly 0.15, and it hits a height going up at 36.48. So again, these are just kind of rough estimates on our plot here, but roughly right around here. Okay, 0.153. I'll put this in brackets just so you can see the coordinate point, 0.153, comma 36.48. Okay, and then it hits the water, looking at our technology, where it crosses that x-axis, and so it looks like it hits the water at 0.426, so just after 0.4, Okay, so not halfway, just before there. And so really this kind of paints a picture for me of where this should be. So I can kind of see my line here where this is going to connect and where this is going to start to cross over. Right, so I've got my value down here at 0.426, comma, 0. So I can sketch this out, and I can actually read some pretty important information from there. So let's take a look at our B problem and see what it asks. What's the y-intercept? Well, we know the y-intercept in this case is 25 centimeters. Okay, which was also its initial height. What does it represent in this situation? So it represents the starting point. Of the frog. Okay, what maximum height does the frog reach? Well, that's our vertex, right? So the frog reaches a maximum height of 36.48 centimeters. It wanted to the nearest tenth, so 36.5 centimeters in max height. When does it reach that height? It reaches it at 0.15 seconds, or 0.2 seconds to the nearest tenth, I suppose. When does the frog hit the surface of the water? So the frog hits the surface of the water 0.426 or 0.4 seconds after it jumps, because presumably the timer starts when the frog jumps off the rock. So off the rock. What are the domain and range in this situation? So our domain now and our range, so we just need to be careful here in terms of our variables. Remember that x is your domain, y is your range. And so our domain now, keep in mind here, is all of our x values that are included in this. And so in this case, I can't have negative time. So it's actually going to start at 0, and it's going to end when it hits the water. So it looks like here our domain would be 0 is less than or equal to x. So x is bigger than or equal to 0, but that same value x has to be smaller than the max time that it takes for it to hit the water, 426 seconds, such that x is in the set of real numbers. Our range has restrictions as well. If I could see here, our height maxes out at 0. It doesn't track it in the water, it just tracks it in the air, and it has a max height of 36.48. So in this case, we've got the same 0 is less than or equal to y, which is less than or equal to 36.48 centimeters, such that y is still in our set of real numbers because I can have all those decimals. Now, the last part here, how high is the frog? 0.25 seconds after it jumps. Well, I've got an equation set up for this. And so remember our equation from that last problem, or from this problem, is h of t is equal to negative 490 t squared plus 150 t plus 25. So h of 0.25 seconds is equal to negative 490, 0.25 squared plus 150 times 0.25 plus 25. So by plugging in that 0.25 seconds, it's going to tell me the height that it's at that time period. So the height at 0.25 seconds equals out to be negative 30.625 plus 37.5 plus 25. And so our height value works out to be, at 0.25 seconds, works out to be 31.875 centimeters. Okay, so at 0.25 seconds, the frog was 31.875 centimeters above the water. All right, and that helps us kind of visualize our problem and what we're dealing with. All right, so I'll get you guys to try one out. We've got A diver that jumps from a 3-meter springboard, it has an initial vertical velocity of 6.8 meters per second. Her height, which is in H, is in meters above the water, and basically is timed after leaving the board, and the diving board can be modeled by this function right here. And so same thing using graphic technology, sketch out the problem, see what the Y-intercept tells you, kind of go through the question, and come back when you're ready to go through it. Alright, so hopefully you had a chance just to kind of sketch out the problem and see what it is. We've got our equation set up, and so we should be able to just model this through. So let's take a look and see what we have here. We have our graph, okay, to start off with, and same thing from before. We have time in seconds, and we have our height, which in this case now is in meters. And so if I'm counting or going through my meters here, I can see from my equation that she leaves at 3 meters for a Y-intercept. So she's leaving right here in 3 meters. So 1, 2, 3, 4, 5, 6, 7. And then the same thing, using my graphing technology, I can start to go through and pinpoint certain values. And certainly if you need a hand with that, then please let me know and I can help you out with the graphing technology piece. So at the end of this, we can see that the diver lands in the water about 1.74 seconds after. So if I start to count at 1.74 seconds and what I have here, basically I can kind of make up a little scale here to use. I'm going to count by 0.4s to go through. So this one will be 0.8, and then this one will be 1.6, and then this one will be 2.4. And so it's just counting by 0.4s as we start to go through each increment. And so the max height that I'm getting here, when I take a look at the vertex in my model with my graphing calculator, is 0.694 seconds over, and it's 5.359 meters high. So 0.694 is going to be somewhere between my first and second notch that I have here, and 5.3 up. So I'm going to be somewhere in here. Okay, and then the landing spot, actually here I'll kind of write out what this is. So 0.694, and that is 5.359. Okay, and again, all I did was just take that right from either from Desmos or from a graphing calculator and just go find that vertex point. And so if you need a hand with that, please let me know. I don't mind helping out to show you how to calculate those. And then 1.74 seconds across, so 1.7 and 0 will bring me somewhere in here. So kind of using the idea of mirroring out a point here, I can kind of see what this starts to look like, right, in terms of its parabola. So that really helps kind of shape my question. So in the A part, it's just saying to sketch it out. Okay, so sketch a function. So here's my sketch. The B question then says, what does the Y-intercept represent? So in this case, the Y-intercept right here tells me the initial height. Okay, so initial height of the diver. Okay, C in this case says, what maximum height does the diver reach, and when does she reach that height? So basically it's asking for this, right? So she reaches a maximum height of 5.359 meters in 0.694 seconds. Okay, D. How long does it take before the diver hits the water? So that's looking for this point. That's looking for my x-intercept where it crosses. So how long does it take for her to hit the water? So it takes 1.74 seconds for the diver to hit the water. And then in my E problem after that, what is the domain and range? How are they appropriate for the situation that's here? So domain, range, remember domain deals with X, range deals with Y. And so in this situation, again, I'm starting at 0 height and 0 time. So 0 is going to be less than or equal to X, which is going to be less than or equal to the maximum time when the diver hit the water, 1.74 seconds, such that I can have all kinds of decimals and everything, so I have real numbers. Y is going to be the same thing, less than or equal to, and then I've got 5.359 meters high, such that Y also can have a whole bunch of different decimal values, so that's also going to be in the set of real numbers. And then at the end here, I've got F, and F says, what is the height of the diver 0.6 seconds after leaving the diving board? So here I've got to plug in my equation, which is going to mirror the same thing from before. So remember I had h of t equals negative 4.9 t squared plus 6.8 t plus 3. So here we're going to plug in my time value of 0.6 seconds, so 0.6, negative 4.9, 0.6 seconds squared. So all I'm doing is plugging in that time value that it asked for into my t's, and then I'm just solving for there. Okay, so 0.6 equals, this is going to be negative 1.764 plus 4.08 plus 3, which looks like at the end this is going to be 5.316 meters high. So I would say something like at 0.6 seconds the diver reaches a height of 5.316 meters. Right? Now our last part here is to write a quadratic function to model a situation. So a rancher has 100 meters of fencing available to build a rectangular corral. And again, it wants us to, this time actually to write the equation, or write a function in standard form to represent what it could be, and then asks us a bunch of different questions from there, like what could the vertex be, and all that kind of stuff. So C even asks us to sketch out a graph for it. So let's start off with A. We've got 100 meters of fencing. So fencing normally means that we're going around the object. Okay, so around the outside. So here we're kind of talking like a perimeter, but notice that it wants us to represent the area of this. All right, so we can start off with this kind of idea because we have perimeter is equal to 2L plus 2W. And so we also have area that's equal to length times width. And we're talking about the same fencing here when we talk about perimeter or area. So we also know that we have 100 meters of fencing altogether. So if I have 100 meters in the perimeter, that's going to be 2L plus 2W. Well, I can make this a lot easier on myself and divide everywhere by 2 to start off with. So 50 is just equal to L plus W. And then I can pick either one of these and let's just rearrange for one. So I'm going to say if the length is equal to, subtract W over to the other side, 50 minus W. Well, what can I do with that L is equal to 50 minus W? Well, I have a function over here of area, and now I know the length is 50 minus W, and I can multiply that by W, right? So I substituted in the length into my area equation. Now if I kind of expand this out a little bit, I'm going to get 50W minus W squared. Or if I were to just rewrite those terms, minus W squared plus 50W, that satisfies my A question. Right? I can get an equation, okay, write a quadratic function in standard form. Okay, I did that right there to represent the area of this corral. So my A question from there really helped me kind of figure out what this is going to look like. So A is equal to, and then again, I pull that equation out, minus w squared plus 50w. And then from there, I can answer a whole bunch of questions. Okay, just coming up with that equation is a big step. So, what are the coordinates of the vertex? And what does the vertex represent in this situation? Well, we have a little bit of a formula that we can use to figure out the vertex. Remember, I can do minus b over 2a. That helps me find the axis of symmetry. That's also the x coordinate from my vertex. So, if I did minus b over 2a, it would be like saying minus 50 over 2 times negative 1, which would be like saying 25. So that gives me an x value for this, okay, or a w value in this case, I guess. And then after that, if I plug that back into my equation, so the area, and plugged in 25 plus 50 times 25, then the area is going to be negative 625 plus 1250, which tells me that the area of this thing is 625 square meters, right? 100 meters of fencing. So I've got meters squared there for my unit. And then 25 would be, my W would be my width, so 25 meters here. Okay, C is then saying, what does the vertex represent in this situation? So, at this point now, if I start to look at my vertex, remember vertexes normally represent the highest point. So my vertex here would really represent the vertex represents, notice I have a negative w squared, that means it opens down, so it has a high point, it has a maximum. So the vertex represents the maximum area. Okay, and then sketch the graph for the function you determined in part A. So now a sketch for this graph. I could have something that could jump up by quite a bit here because I have to get up to 625. So maybe jump by hundreds. So 1, 2, 3, 4, 5, 6, 7. And across my bottom, I know that I'm going to 25. So I'm going to maybe jump by 5s here. Okay, and give myself a little bit more space kind of coming across here. Okay, so 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. Okay, just by 30 and then 40 and then 50. Okay, just kind of showing how I'm skip counting here to go by 5s, and then these ones are going to be 200, 400, 600, where this axis is my area, and that's going to be in meters squared, and then the bottom axis is my width, and that's just in meters. So I know that this thing is starting at 0, 0, but remember from my equation here I can actually take a look and see what my roots are going to be, right? So if I were to take a look here at this equation, right, I could factor out that W, how I started with originally. Okay, so if I factored out the W, minus W, then I'm getting W minus 50. Right, so then I can see here that for this function to equal 0, W would have to equal 0, or W would have to equal 50. So that actually tells me where it crosses the x-intercept in 2 spots. And then at 25 meters, I knew that I went up as high as 625. And so from here, then I can start to visualize kind of what this looks like in terms of my parabola shape, right, to sketch out what the graph would look like. Okay, so D says determine the domain and the range for this situation. So, okay, so the domain and the range, remember domain is all of your x's and range is all of your y's. So in this case, my domain is going to be that 0 is less than or equal to x, which is less than or equal to 50, such that x is in the set of real numbers because I can have decimal meters, and y is going to be my height, and so it's starting at 0, but it can only go as high up as 625 meters, such that y is in the set of real numbers. And then E starts to say, to identify any assumptions you made in modeling the situation mathematically. So any assumptions that we make in the problem, well, one main assumption would be to assume that we used all of the fencing. And so maybe the person didn't use all of their fencing, in which case that would change the model of our equation because we started with that 100 meters. So from this problem, hopefully you can kind of get a sense of how some of these word problems are done. And we'll be practicing some of these using some of that graphing technology. So feel free to use Desmos or get a graphing calculator to try some of these out. And good luck, and let me know if you have any questions.